My name is Jakub Chmura, as I was introduced, and I'm a software engineer at Software Mention, where I work in our in-house AI team. And today I wanted to talk to you about what we think the future of AI is going to look like, and why it might not be distributed the way you think it is. So, about 3 years ago, ChatGPT went viral and changed everything. Suddenly, everyone was generating code, talking to AI, transcribing meetings, and it all felt pretty magical, but under the hood, almost all of these services operate in the same way. So you send a request to the GPU cluster that costs more than my house, and a few seconds later, you get your response back. And we all use this daily, but unfortunately, it does have a couple of big drawbacks. So let's start with cost. While consumer-grade subscriptions like ChatGPT Plus seem affordable at $20 a month, the reality behind the scenes is pretty different. So to host large models, you need dozens of high-end GPUs, which does not account for model training and maintenance, which is also a very big cost. You have to pay for electricity to maintain the GPUs. You have to provide scaling for your users, and these costs inevitably have to get passed down to users. So privacy is another major concern. Every API call potentially exposes your data to third parties, and there's often unclear language on how your data is used for further model training. So for businesses handling sensitive information, this creates some compliance issues. Your data also gets stored in some third-party company database, which increases the chances of your data getting leaked. Then there's scaling. You probably know how hard it is to scale video infrastructure, so you can imagine adding a ton of GPU computations on top of that. And during peak usage, your users are competing over the same resources, which can lead to rate limiting and potentially degraded performance. There's the connectivity requirement. So no internet means no AI, which can be problematic for some use cases or applications, mobile applications or users with poor internet connectivity. Then there's latency. So using cloud AI obviously requires you to transfer data over network, which you probably know can get complex and introduces some latency. So what is the solution? We believe you have it in your pocket, and it's your phone. Each and every one of us carries around a pretty powerful compute engine in the pocket. So maybe we can use that compute engine to power AI models. In this talk, I'll show you what is possible today and briefly describe how it works under the hood. But before I do, let me introduce you to how we even got to this point. One of our first projects was about disappearing objects from video streams in real time. You can think of it like a real-time invisibility cloak for anything you don't want in your stream. In our case, that was models. We spent quite a bit of time trying to get the best model architecture so it fits within what we considered a real-time constraint. And we finished with a pipeline that could localize an object, erase it with visually plausible content, and then stream the resulting frame back to the user. All of this functioned at close to 30 FPS on a consumer-grade GPU, NVIDIA GPU. The problem with that was that we could only maintain up to 3 connections at a certain point on a single GPU. Here's a demo of how that looked like. You can see the bottle is not there, and it's sort of erased with what would have been there if not the bottle. Once we were done with online inpainting, we wanted to see how we can employ a similar strategy for offline deployment. So processing full video streams would be too computationally expensive to do on a phone, so we decided to tackle a different problem. We wanted to create a photo editor app that would erase objects from images using a reference image. So that would hopefully help the model, make it much easier for the model to sort of know what to fill in the missing area. So given our previous experiences with similar problem, we optimized the architecture. We had to deploy it on mobile somehow. So we were searching for the right tool for the job. After extensive research, we found out Executorch, which turned out to be our favorite tool right now. And we successfully deployed it. And all of those experiences led us to a point where we are pretty excited about on-device AI, and we started digging deeper. Cool, so now let me introduce you to some tools that might help you build stuff as a multimedia developer. So there's a lot of open source frameworks for web, mobile, or other platforms that let you run AI locally. If you're doing transcriptions, which I suppose many of you are, then I'm pretty sure you're using some third-party service or hosting your own backend, which you send audio to. What you can actually do instead is try running it directly in the browser. For example, a very popular model, which has been mentioned today a couple of times, Whisper, can be easily run with the help of a tool called Transformers.js on a web GPU. And before you think it's slow, here's a demo of it running on my MacBook. Unfortunately, you cannot hear it.
Speech in real time without sending any data to external servers.
Okay, so hopefully you can see the latency is pretty small. It's capable of processing at around 80 tokens per second, which is pretty fast. If for some reason you don't want to do this locally, what you can do instead is try running voice activity detection locally, which is usually more lightweight, and only stream relevant audio chunks to your backend. This way you possibly reduce redundant calculations or reduce hallucinations. On that note, since speech-to-speech has been mentioned before, there's a very cool model called Hibiki that lets you do speech-to-speech translation on a mobile phone. It is very small, and I recommend checking that out. Then there's computer vision. So I'm pretty sure a lot of you are familiar with the famous feature from Google Meet that blurs your background. This has already been said by Chris, but Google is pretty open about this, and we know that this works entirely on device. The underlying model here is responsible for detecting the background, and then everything that's classified as background is blurred, or some specific picture is applied to that area. The fact that on-device AI is a part of one of the biggest products out there shows that it's no longer fairy tales, but it actually reaches millions of users. Here's how it works. The video texture is taken from your browser, and it is passed to a MediaPipe WebAssembly pipeline. So the pipeline is responsible for doing machine learning inference and refining the segmentation mask. So a common practice in computer vision is to downsample the image before passing it to the machine learning model, which greatly reduces the number of computations. So the actual model can run faster. After the inference, you just upsample the output. In case of segmentation, you also need to refine the output mask because it has rough edges after the upsampling operation. And below you can see a performance chart. As you can see, it's running at 70 FPS, the entire pipeline, on a MacBook Pro 18, which is Intel-based, so not that new. And they also have smaller versions of that model for lower-end devices. Also, this feature is actually coming to the Media Stream Track API, which is cool. But it's not just about transcriptions anymore. Recently, VLMs have been on the rise, and vision language models are able to understand both text and image data. So, for example, if you show them your camera feed, they should have a basic understanding of what is going on within each frame. So Apple has recently released a model called FastVLM. It contains just 500 million parameters, which makes it small enough to run in your browser or on your phone. You can see a quick demo of it. As you can see, it is able to do OCR or count fingers. This shows that as research progresses, small models are becoming more capable, and you can see on the screen that it's pretty good. You can also run standard LLMs too, like Llama 3.2 or Qwen 3. They are all already achievable. Big tech companies are investing a lot of resources into frameworks and adoption around on-device AI. And Google has recently launched a set of APIs available natively within Chrome that let you do some pretty cool stuff. So for example, you can translate text from source language to target language. You can summarize blocks of text, or you can ask it to write something. So you get everything built in within the browser. You no longer need to compile anything to WebAssembly yourself and have all the headaches. This is made possible by introducing multiple expert models and Gemini Nano under the hood, but this is currently under a feature flag. This is not just a software shift. It requires changes to the bare metal, and Apple has integrated neural processing units since 2017, which is a specialized hardware for AI tasks. Their performance is measured in TOPS, which is trillions of operations per second. This chart shows how TOPS have grown with each flagship chip, and the steady rise shows that if this trend continues, that devices in our pockets will become even more capable than they are now. So another example of big things in the space is obviously Apple Intelligence. Apple has already integrated multiple on-device AI models directly into iOS and macOS. So, for instance, we have the object segmentation model, which lets you take an object from a photo by tapping on it and localize it on a per pixel level, so you can see it on the screen. A very notable feature is also grammar correction. You obviously don't want your private chats to be sent over to third parties, so this is very nice that they're doing this locally. This is honestly my favorite, semantic gallery search, which allows you to look through your image gallery by using natural language. So you don't have to scroll through thousands of pictures if you're looking for something. This is made possible by models such as Clip or Apple's Mobile Clip. The new AirPods Pro also feature a live translation feature during a phone call, which is all computed on device. What is very exciting as well is that Apple has made it possible to use those models by providing native SDKs. This means that you can use AI that's built in your system within minutes with no headaches. So there are some things you need to consider before you use any of these tools. Obviously, since you're running it on a client's device, there's a limited computational power. So therefore, you can't run models as smart as the ones you can run in the cloud. You usually have to make a trade-off between performance and the quality of the model. And if you're continuously using large language models or other large models, then you also have problems with high power consumption. If you want to release another version of the model, this might be problematic as well, since it usually requires the user to download the model all over again. There's also pretty high development complexity compared to what you get in Python or other languages with mature machine learning ecosystem. Lastly, the performance is dependent on the device that it's running on, meaning that some users may experience poor experience while other not as much. So I mentioned Executorch before. Now let me give you a little introduction to the tool and how it works under the hood. So Executorch is an open source toolkit that's developed by Meta for enabling on-device AI machine learning features across edge devices, such as microcontrollers, mobile phones, wearables, whatever. What is exciting about Executorch is that it offers hardware acceleration, meaning that at runtime you're actually calling the native implementations for machine learning operations. It is also PyTorch native, meaning that if you train your models in PyTorch, you never have to leave the ecosystem from training to production, which is very beneficial because the third-party export tools sometimes are not as reliable as we would want them to be. It is also highly customizable. You can even control how memory is allocated before the actual runtime. So what needs to happen for your model so you can run it on an edge device? So the entire process consists of two major steps, ahead of time and inference time. And ahead of time, you can think of it as compile time. It all happens in Python. And the inference time is basically runtime, and it happens in C++. One of the main design choices of Executorch is to offload as much work as possible outside runtime, so you don't have to do this at runtime, effectively saving precious seconds. The AOT part produces a high-performance flat buffer binary containing Executorch instructions, which are then executed by the runtime on the client's device. So here's the runtime part. The exported program is deserialized and loaded into the runtime. It contains symbolic operator names, such as add, multiply, and so on. And the runtime maps these symbols to actual C++ functions through the operator and backend registry. So you have to link specific backends and kernel libraries against the runtime, depending on what platform you're targeting. Then it sequentially executes instructions. And what makes this run everywhere, from iOS to bare metal, is the platform abstraction layer at the bottom. So it abstracts away all of the system calls for memory, logging, and timing. This way the runtime can function even when there's no system to call to. Now let's see the code that is needed to export your model. So the AOT part starts with a PyTorch model. I'm using here a very simple example with a single linear layer, but this could be your audio classifier or whatever you need, basically. Once you have the model, you need to pass it through a process called torch export. So torch export takes your neural network and breaks it down into basic building blocks, such as addition, matrix multiplication, convolutions, and these operators form a computational graph that represents how data flows through your model. Once we have the exported model, this is where most of the mobile optimizations kick in. So one example of performance optimization is quantization. Usually the weights and activations of the model are stored using 32-bit floats, which can be reduced to lower precision, trading off some quality. The most important part here is the delegation part. This means that you train your models in PyTorch, but at deployment you can actually call Apple's or Qualcomm hardware accelerated operations. So the takeaway is that you get native performance without learning 5 different frameworks. And if a backend doesn't support a certain operator, it falls back to CPU. So in this code snippet, you see we're taking out the torch exported models, and the XNNPAC partitioner is basically responsible for choosing the parts of the graph which can be delegated to XNNPAC. And finally, we're just saving it to a file. And where do we fit in this ecosystem? So for the past year, we've been working on React Native Executorch. Executorch itself is a great tool, but it does require some setup, especially if you're coming from a React Native background. First of all, you have to set up and link all the needed libraries. You need to export your models. You need to make sure that your pre- and post-processing are rock solid. This is time-consuming and requires deep experience with native code and machine learning internals. We want to abstract this away by providing a set of JavaScript APIs that just work, and you can set it up within minutes instead of weeks. Here's a list of features that are currently supported. One of the most notable ones are, of course, LLMs, amongst which we support Llama, Qwen. We have tool calling, Whisper, text embeddings, OCR, and many more. But we're actually aiming to go beyond this, and we want to create an entire ecosystem for on-device AI experiences. So we have already created a small extensible library called React Native RAG, which lets you enhance your LLM's knowledge with external documents, completely offline. This means that you can upload some third-party documents to your LLM as a context, and you're not sharing your data with anyone. So here's all the code you need to get started, and to install, you just npm install. As you can see, we're doing a bunch of importing, then we're basically calling the useLLM hook, and we're defining the handle generate function, which defines a chat variable, which is an array of objects basically representing a chat turn. Lastly, we're just calling the generate function, and that's it. If you've used the chat completions API by OpenAI, then this might seem familiar to you. We were heavily inspired. Whether you are a React Native developer or not, we got something cool for you. We created an application called Private Mind that demonstrates what is possible today with local workflows, and released it to the App Store and Google Play. So I highly encourage you to check it out and play with it. So let's do a demo of the RAG feature. So I have a chat here with Qwen 3 1.7b quantized. And I'm going to pass it a PDF file, which is basically the RTC.ON website. So I can select that. And let's ask it, what is the Executorch workshop going to be about? And before I do that, let me turn on airplane mode. OK. So it needs some time to think. OK. Once it gets started, it's OK. That's actually pretty true. I don't know which one of you was on the workshops, but it looks right to me. And when is the conference happening? Yeah, that seems about right. And yeah, this is all open source, by the way. You can check it out on GitHub. And on-device AI is not perfect for everything yet, but small models are getting more smart, and hardware is getting faster, and new doors open daily. So it's up to you if you want to use it today, but you should definitely keep an eye out on what's happening in the space. Thank you.
Thank you, Jakub. Are there any questions about this fascinating stuff? One question over there, gentleman in the back.
Quick question. Did you try to convert PyTorch models to native CoreML models and use it within native environment?
We haven't directly converted PyTorch to the CoreML models, no, but actually Executorch does offer a CoreML backend. So effectively, with Executorch, you can call CoreML's native stuff. So yeah, hope that answers your question.
Yeah, thanks.
Any other questions?
Great talk, man. Thank you. I think this is more of a comment rather than a question, but I think the cool thing about all the stuff that runs on local devices, particularly on phones, it can actually be applied to server implementations to make it actually cost effective, which I think that's where the future is going. But yeah, highly distributed, whether it's on client or not, is definitely the direction.
That's true. Thank you.
Unless there are any other questions, let's wrap it up with a round of applause for Jakub.